this website here. The review will be from 11 to 1 p.m. I'm going to leave about 10 minutes of time for questions at the end. So if you have any questions that are major, then that would definitely be the time to ask them in the last 10 minutes. But also kind of as we go through, if you have questions, we can kind of talk them over, okay? Let's see what else. So really quickly, is everybody here for Chem 1B? Okay, because I know there was a bit of a mix-up with the rooms, and so I put that my room is in Cape, Florida, but then now there are 2 parts to it. So I just want to make sure everyone here is in the right half of the room. And, oh yes, this is a good idea. I'll do this now. So I'm going to pass out some surveys for everybody. If everybody could make sure to fill these out before the end of the review. You don't have to wait till the end, but if you want to, you can. But really, whenever you feel like you're ready, you've seen kind of how it's going and have a particular, kind of feel out what it's going to be like, you guys can then, let me make sure, yeah, these are the right ones. You guys can then start filling it out, okay? So you don't have to wait till the end. I know some of you guys have stuff to go to right after this, so I don't want to hold you up till the very last minute. If you guys have extras and you notice somebody doesn't have them, just feel free to pass them around. Here you go, guys. Here you go. Yeah, thank you. So let me go ahead and get officially started. So for those of you who don't know me, I am the Chem 1B tutor at SARC. My name is Timothy. I know a lot of you guys have come to my tutoring session, so it's good to see some familiar faces. Let me know if you can't hear anything. I'll make sure to speak louder, or if it's too loud, I'll speak lower. So welcome to all you guys, and also welcome to everyone watching right now on the live stream, and also those of you who are going to watch later. Some quick notes again, you can find this review document at this website, and also you can go back later after this review and find this review on YouTube, on the UCF SARC YouTube. Some of the questions I pulled from, just a couple of them, I pulled from another tutor's review sheet because I thought they were really good. So I'm going to give credit to Laura Sawire. She's another SARC tutor of ours. And I want to let you guys know that most of these questions are from past ACS exams or some kind of ACS review material. So if you guys are worried about the ACS, this should give you a pretty good feeling of what it's going to look like. Just know this review is not comprehensive, so it doesn't cover every possible thing that you could see. So make sure to go back and review on your own, okay? This is not going to cover everything. I know a lot of you were asking me whether or not this is going to cover Chem 1A and Chem 1B, and the answer is yes. It'll cover a lot of Chem 1A stuff as well. Okay, so hopefully this will be a really good refresher for you guys who, I know it's been a while since you've seen Chem 1A stuff. But make sure to review and make sure to look over past questions from the ACS exam just to make sure you have a good feeling for what's going to be happening. Okay, so let's go ahead and get started. Are there any questions starting out? Okay, give me 1 second. I don't know, I see a lot of people walking in and having to sit on the floors, so thanks guys for bearing with it. I hope that maybe they'll pull in more chairs. When the stream guy comes back around, I'll ask him if he maybe could pull in some chairs. Okay? Okay, so if there are no questions, we will go ahead and get started. So here, for question 1, which element is represented by, here, X? We don't have any specific element, we're looking for that. And we're given some information here. 2 numbers can, oh, it's a little, let me see if I can bring it in a little bit for you guys. It's a little easier to see. There we go. So does anybody know, what's this bottom number? What is that number called? If you want, there's a little bit of a hint over here. What's this bottom number called? Can I hear it a little louder? The atomic number. What is the atomic number? The number of protons. And then what's the upper number over here? mass number, which has what? Protons and neutrons. So this is a really, really old Chem 1A topic. Make sure you guys go over all the different topics, okay? This is going to be important for the exam. So here, when we're looking for the element, remember that using a periodic table, sorry, it's getting really loud and really low. Let me try to keep it pretty consistent. So remember, when we're using the periodic table, guys, we can look at here the atomic number, and that'll correspond with a number on the periodic table. Okay, so here when we're looking for this element, we can see that the atomic number is 24. So I'm going to go to the periodic table and look for element 24. And if you see here, chromium is element 24. And so here, D is our answer. Okay. Any questions about that one? Okay. On to the next one. Same thing here. We have our mass number and atomic number. And we're looking for the number of neutrons. So remember that our mass number has both protons and neutrons, and our atomic number has just the protons. So if we're trying to find the number of neutrons, we can just take here the mass number, which is 37, and subtract from it the number of protons, which is our here atomic number, 17, and that gives us 20. So that is the number of neutrons, making the answer here B. What if I asked you how many protons are in that element? What would the answer be? Let's see here, 20. Why would it be 20? Okay, neutrons and protons have the same number. So two things in an atom do have the same number usually. It's not the protons and neutrons though, it's the protons and electrons, okay? So thanks for putting it out there. I hope that's going to refresh your minds. How many protons do I have in this sample? 17, remember the atomic number. How many neutrons are in this, electrons are in the sample? Okay, so here, somebody pointed, we kind of talked it over that protons and electrons are the same, which makes that the electrons are going to be 17, but here, what do we notice about the Cl? It has a negative charge. So are we adding an electron or taking away an electron? Adding, we're adding a negative charge. So 17 electrons, but then we have the negative charge, so that makes it 18 electrons. So 18 electrons and 17 protons. So make sure you guys can do all that for the ACS exam, and also really for your professor's exam. Okay, I hope that that's a good refresher. And quick note here, the X is just the chemical symbol. We kind of talked about that up here in that problem. Okay, now for number 3. So here the element X occurs naturally to the extent of 20%, and here we're given a mass number of 12, and 80%, and we're given a mass number of 13. And we're asked to find the atomic mass of the element. Okay, does anybody remember what the formula is for atomic mass? So atomic mass is we add up here, we add up all of or two things here. So we add up the fractions of each element's mass. So here, fraction and the mass number. Okay, so this is a formula you're going to want to know. I know that, again, another old Chem 1A topic. So I know it's been a while, so I hope, again, this is going to be refreshing some of that old stuff. Okay, so I just add up the fraction times the mass number of each thing. Here I've got two things. Let me go ahead and add these up. Here, for the first piece, can somebody tell me what's the fraction that we find this? I heard 20. 0.2. Okay, 0.2. So remember, guys, here, this is a percentage. To convert to a fraction, we can move the decimal place over 2 points or 2 spots. And here, that becomes 0.2. Okay, so that's our fraction. It's really easy to forget this and just multiply by 20, okay, instead of going to 0.2. Just be aware, guys, that on my past ACS exams, I've seen that if a mistake is really commonly made, that mistake will actually be one of the answer choices. So let's say here that you went and used 20 instead of 0.2 for the fraction, and you got an answer, it would probably match up with one of the answer choices. So you have to be extra careful because you don't have that checker where if you get it wrong, it'll give you no answer matches. So make sure that you really know this stuff so that you don't get fooled by that. And what is the mass number for the first element? It's a little small. There, that should help. Can somebody shout it out? 12, perfect. Sorry, I keep getting really loud. Let me try to pull it in a little. Okay, what's the fraction for the other element? 0.8, perfect. And what is that multiplied by? 13, perfect. And let me see what I got here. When I did that, I got 12.8. So that is the atomic mass, and that's C. So if you guys look in your periodic tables, well, you don't have to look right now. I'm just bringing this up here. The atomic mass is what you see on the periodic table. That's the molar mass. You see all those fractions, 20% and 80%? Let's say we have carbon in nature, and we're trying to find its overall atomic mass. We'd find what percentage we find carbon with one particular mass, and the percentage we'd find another carbon isotope with a different mass, and we'd take the average. We'd find what is carbon's average atomic mass, and that's the molar mass you see on the periodic table. Okay? So this is just combining the different pieces, the fractions that we see, the different isotopes in nature, and putting them together into one number. Okay, and we just add up those, get the average of those two by finding the fraction and multiplying by the mass number and adding them all up. Any questions about that one? Okay, let's move on. Here is the formula. So in the review sheet, guys, I have a lot of different formulas and charts that should really help you. So I'd recommend going back and printing this out, trying out the problems, writing down the formulas. They're going to be a lot more than what I go over, but it's going to be a really good start if you're just trying to go back and see what there was in Chem 1A. Okay, so for this problem, a compound is found to consist of some percentage of sodium, some percentage of boron, and some percentage of oxygen. What is its simplest formula? Okay, so this is another old Chem 1A topic. I remember this one was particularly tricky when I took Chem 1A, but if we go back, think back to what we did back in Chem 1A, here we've got 3 pieces that make up some kind of compound. Here, these are the possible compounds. They all have sodium, boron, and oxygen, just like here, sodium, boron, and oxygen. But we just don't know how many atoms of each type are in the compound. So, for these problems, what we have to do is we have to look at the percentage of each one. So here, 34.9% sodium. We have 16.4% boron and 48.6% oxygen. If you guys hear the noise there, sorry, they're doing renovations, so if you hear the hammer fall, that's what you're hearing. I'll try not to let it distract me. Let's all try to stay focused on this. Okay, so we can't really work with percentages, so the first step is to always go to something we can work with. And here what we can do is assume that we have about 100 molecules or so, or 100% of this compound, and so we can assume that that 34.9% is 34.9 grams of sodium. Okay, and here 16.4 grams of boron and 48.6 grams of oxygen. Okay, so that's the first step. That's like a little trick to do to get to something you can work with. And now we need to get from grams to moles. Okay, how do we get from grams to moles always? Yeah, the molar mass. Perfect. So let's go ahead here. I'm going to pull it out for you guys. The molar mass of sodium is 23. Okay. Here, the molar mass of boron is 10.81 grams. And let me shift this down a little bit. 48.6. The molar mass of oxygen is here 16 grams. Okay, so when I solve this out and get to our moles, I get 1.52 moles of sodium and 1.52 moles of boron and 3.04 moles of oxygen. Okay, so what is the next step? That's exactly right. You look to the smallest moles and divide all the other numbers by that. So let's really quickly write out our general formula. Here, Na, and we have 1.52. Here, boron, we have 1.52. And oxygen, we had 3.04. If I divide by the smallest amount, which is 1.52, here, I'm going to get Na. You see here how something divided by itself is just 1. So for Na, I just have one of them. And the same as for boron. And for oxygen, I get 2 when I divide those out. So if we look in our answer choices, that is A. Any questions about that? Yes, Becky.
Does it not matter that oxygen is diatomic, so you wouldn't need variance in.
That is a good question. So here they didn't say oxygen gas. They just said oxygen. So Becky's bringing up something that was important that we learned in the gas chapter, where whenever we say oxygen or hydrogen or fluorine, we have to remember that the thing is diatomic. Here they tell us that we have some percentage of it, and then we can go to grams of that. So that's the total grams of oxygen. So that takes into account every bit of the O2, so we don't have to really worry about for this one. And we can just multiply by the standard molar mass. We don't have to double anything, because they told us exactly how much oxygen is in there. Does that make sense? Okay. Any more questions about this? Okay, so on to the next one. What is the molar mass of an ideal gas if we have some amount of the sample of this gas that occupies a particular volume? Here we have a particular temperature and a particular pressure. Okay, so we're talking about a gas, so we should think back to all the different options we have for formulas for gases. We're trying to calculate something. What do you guys think we can use to get one piece of the puzzle? Yeah?
Use the PV equals nRT for me.
Perfect. PV equals nRT. Here, one hint for that, guys, is we have a temperature, a pressure, we have a volume here. When we're given all those pieces, it usually means for a gas that we're going to be using the ideal gas law, or the PV equals nRT. Let me write that out. PV equals nRT. What are we trying to find again in this problem? What's the goal? To find the molar mass. So, what is the formula for molar mass? You don't have to raise your hand, just shout it out. Mass times RT. Oh, I see what you're saying. You're solving for the moles. I'm saying molar mass. What's the general something over something? Grams over moles. But I actually will call on you for the next part, okay? Grams over moles. So, do we have a gram already? Do we have our mass?
Yes.
Yes, they gave it to us. What do we have left to find? The moles. And how do we get the moles? We use the ideal gas law. I heard some of you guys saying it. Okay, so to get the moles here, I'm going to solve for N. And what did you say it was? PV over RT. Perfect. And I'm going to go and plug everything in. What is our R? 0.08206, perfect. What is our T? I heard someone whispering very lowly that we have to convert to Celsius. Guys, feel free to speak up, okay, so that everyone can kind of hear what you're saying. Here we're going to have to convert to Kelvin. And when I do that, I get 308 Kelvin. And so here, let me plug this in. And let's see here, now we need our pressure and volume. So what is our pressure? Could you say it louder?
You have to convert it to atmosphere. You divide it by 760 millimeters.
Perfect. You divide it by 760 to get ATM. So here, 1 ATM is the same as 760 mmHg, which is the same as torr. And when I do that, I get 1.04 ATM. Remember, guys, that every time you use the ideal gas law, you have to convert to Kelvin, atmospheres, you have to make sure you have moles, and then you have to also remember the gas constant, 0.08206. Here, so I'm going to do 1.04 for our pressure and our volume. Oh, sorry, for our, pressure. And what about for our volume? What volume do we have? Yeah, 0.3 liters. Again, we have to convert here to liters, so 0.3 liters. And when I solve this out, I got 0.0123 moles. Is that our answer? No, what are we trying to find? Molar mass. So here, let me go back to my molar mass formula, which was grams over moles. I'm going to pull out the grams. I'm going to get my moles that I found. 1, 2, 3. And when I do that, I get 50.5 grams per mole. And that is right over here. Any questions about that one? Yes?
Are we going to be given the constant R?
I think you guys are given your constant R on the ACS exam. At the very front, there's a cover sheet with a periodic table, the different constants and formulas you're given. I think you guys can go online and look up the things that you'll be given. So you look up ACS cover sheet, and it'll show you a list of like all the things you'll be given.
Is that for all
I think so. The ACS is a standardized exam, so I believe it's the same for everyone. I'm not sure though, so if you want to be sure, I'd say look, ask your professor about that. Okay. So for this one here, a 30.5 gram sample of glucose contains how many atoms of carbon? Here, so we're given a certain amount of glucose, and we're trying to find the atoms of carbon. So we're going to have to do a lot of conversions and dimensional analysis. That's a big part of your exam, so make sure you guys get some practice with that. So for this problem, it's kind of hard to figure out where to start. I'd always recommend when you're given some kind of amount, like a certain amount of grams or moles, you always want to start with what they give you and then go from there. So we have 30.5 grams of C6H12O6. Okay. So to be able to go from our glucose to carbon atoms, we're going to have to get to moles at some point. Okay, to really convert between different things, usually you have to get in moles. Let's see here. So how do I go from grams of glucose to moles of glucose? Perfect, molar mass. And I have it for you guys here. It's 1 mole per 180.2 grams. And that is, okay. Okay, so now we're out of grams and we're into moles of glucose. How do we relate the moles of glucose to carbon? I heard, how many moles of carbon do I have in glucose? 6, perfect. I can see here by the number, 6 moles of carbon in 1 mole of glucose. Okay, here I'm getting rid of our moles of glucose. Now I'm in moles of carbon. What is my objective? I'm trying to get what? Atoms of? Okay, perfect, atoms of carbon. How do I go from moles of carbon to atoms of carbon? Avogadro's number, perfect. So, the number is 6.022 times 10 to the 23rd atoms per 1 mole of carbon. Here, remember, you guys can relate atoms and moles to any element. It doesn't have to be carbon. It can be fluorine. It could be hydrogen. It could be oxygen. Here, we need it for carbon, so we're using atoms and moles of carbon. Okay, so moles cancel out, and I get to atoms. And when I solve this out, I'm going to get 6.12 times 10 to the 23rd atoms of carbon. And that answer choice is B. Any questions about that one? Okay, I'm going to move on to the next one. Let me see how I'm doing on time. Okay. So for this next one, what is the mass percent of carbon in dimethyl sulfoxide rounded to 3 significant figures? So if we remember, there's actually a formula for mass percent. Can you guys tell me what it is? You're exactly right. Here on the bottom we have the mass of the compound, the total mass. Here, and that's under or divides the specific thing we're looking for, which is here, mass of, and we're looking for the carbon. So the mass of the carbon divided by the mass of the compound times 100 to get that percent. Okay, perfect. So now, for this one, I have to go ahead and get the mass of the compound and the mass of carbon. And for this one, I can use the formula they give me, C2H6SO, to get the mass of each component. Okay, so let me show you here. Here I have 2 moles of carbon, which, using its molar mass, 12 grams of carbon here, I get 24 grams of carbon. Now I'm going to look at the hydrogens. I have got 6 moles of hydrogen here. See that here? And I can multiply by its molar mass, which is just 1, to get here 6. And then I can take my, how many moles of sulfur do I have? Perfect, 1 mole of sulfur. Multiply it by the molar mass, which is 32 grams per mole. And when I do that, I get 32 grams of sulfur. And now I'm going to take my oxygen, which I only have 1 mole of, multiply by its molar mass, and get 16 grams. Okay, so now I'm going to take my mass percent, and I'm just going to put in the values I found. So here, what is the mass of my carbon? What was that? Oh, sorry, let me move it over. 24, perfect. 24 grams. What is the total mass of the compound? Perfect, thank you for being quick about that here. 24 plus 6 plus 32 plus 16, and I heard it was 78, which I got as well. And I need to multiply by 100 to get that percentage. And when I do that, I get 30.7%. So that's this one right here. Okay, so here I found the percent, or the mass percent of carbon in a compound. I remember when I took the ACS, I saw 2 of these problems, and I forgot how to do both of them. Okay, so make sure if you guys see this, to remember how to do these to get practice so that you're solid when you see it. Okay, so now for this one here. Antimony reacts with sulfur according to this equation, and it's asking for the percent yield for a reaction in which we have a certain amount of some Sb2S3, the product here, produced. And they give us the amount of reactant they used, and they say we have excess sulfur. So looking at this problem, do I know my limiting reagent? Yes, I do. Could somebody tell me, what is my limiting reagent? What? I hear some people mumbling it. Could I hear someone shout it out? Antimony, Sb. They tell me I have excess sulfur, so I know that sulfur is not my limiting reagent because I have extra of it. Okay, remember when I get percent yield, there's a formula for it, and it is the actual yield in grams over my theoretical yield in grams, all times 100. Okay, do I have my actual yield given? Can somebody tell me what's the actual yield? 1.40 grams, exactly. They tell me that when I do this reaction, I get 1.40 grams of my product. So that tells me that's what I actually get. That's my actual yield. Okay, so 1.40 grams of Sb2S3. And how do I get my theoretical yield? I have to look at what? My excess reagent or my limiting reagent? Limiting reagent, perfect. Okay, and that was which one? Antimony. Here, I need to get grams of antimony. So, let me look here. We have a certain amount of antimony. Oh, sorry, so I said we need to get grams of antimony. To get our theoretical yield, we need to use the amount of limiting reagent we have, which is 1.73 grams of antimony, SB, and we need to find out how much product it would make theoretically if it completely reacted, okay? And we can find that by just using dimensional analysis. So using 1.73 grams of antimony, I can get this to moles first. Antimony moles, and the molar mass is 121.8. Now I need to go from moles of antimony to moles of my product. How many moles of antimony do I have in that reaction? Perfect. 2 moles of antimony. And how many moles of product? 1. Sb2, S3. And when I do that, remember I need grams of my product, so I'm going to use the molar mass of the product, which is given up here. And that is 339.7 grams per mole. And when I solve this out, I get 2.41 grams. Okay? What is this number, my actual yield or theoretical yield? My theoretical, perfect. And that goes on the bottom. So 2.41 grams of my product times 100 gives me 58%, which is this one right here. I remember this being a really important problem for the ACS. I think you guys can pretty much expect to have some problem where you're asked to get the theoretical yield or maybe the percent yield. Okay, so make sure you practice this because I know it might have been a long time since you've seen this. Any questions about that one? Okay, on to the next one. This is actually the same exact problem, okay, or a very, very similar. It's just the same process. So I'm going to skip this one for now, and if we have time, we'll come back to it. I want to make sure we don't run out of time so that I can get to a lot of problems for you guys. Okay, so for this one here, for the following reaction, which element was oxidized, reduced, and determine the oxidizing and reducing agent? Remember that anytime we're doing balancing redox reaction, oh, I don't know if you guys don't do that. Sorry, that's Chem 2. Anytime we have to figure out if something's oxidized or reduced, or find the oxidizing or reducing agent, we always have to begin by assigning oxidation states. And remember that there is a set of rules for that. I included them in the review packet, so if you go back, you can find them there. And we start by assigning oxidation states and seeing how they change from the beginning of the reaction going to the end, or from reactants to products. So, based on rule number 2, it tells us that anytime we have an ion all by itself, the oxidation state is exactly the same as its charge. If you look here, I is all by itself, and it has a charge of -1. So its oxidation state is what? Can I hear it louder? -1, perfect. And is there any other thing I can right away tell what the oxidation state is? Yeah, CR. Oh, not CrO4 because it's not. Yes, CR3. Here it's all by itself. Here, what is the oxidation state? +3, perfect. Rule number 1 tells me that anytime I have one type of element all by itself, without any charge, it will have a particular oxidation state. Do you guys know what that is? What's the oxidation state of a free element? Perfect, it's 0. So it's one type of element, and it has no charge. So that means it's a 0. Anytime we see a compound or something with more than one type of element, we have to break it up using rule number 3, which tells us that I can add up the oxidation states of all the atoms, and their oxidation states should equal, or do equal, the overall charge. So if I add up the oxidation state of chromium and all 4 of those oxygens, I will get -2. Okay? There's also a rule, rule number 5, which tells us that oxygen usually has an oxidation state of -2. So going back up here, there's nothing for chromium. Chromium is a transition metal. There's no rule for the oxidation state of a transition metal. So anytime you see a transition metal, you're probably going to have to figure out what the oxidation state is by solving something. And here, if I plug in that -2 for oxygen, here, I can solve for what the oxidation state of chromium is. Here, this becomes -8. So what do I need to add to -8 to get -2? 6, perfect. And you can actually solve this out by, moving it over. But I just want to, here, sometimes it's a little easier to just look at it. So, +6. And here, this tells me that +6 is the oxidation state of chromium. What's the oxidation state of oxygen? I heard -8. If they asked you on the exam what the oxidation state of oxygen is, they aren't asking for the oxidation state of all the atoms added up. They're saying of one oxygen atom. What's the oxidation state of a single oxygen atom in this compound? -2. So the answer would be -2. But they will have a -8 there as well. So a lot of people are going to get tricked because they're going to try to go for the -8. But they're asking for just the oxidation state of one atom. So the answer would be -2. And if we compare both sides of the reaction, I can look at the I going from the reactant side to the product side. Can you guys hear me okay in the back? Everybody, can you guys hear me? Okay, so I don't need to speak any louder. Okay, so here, is -1 to 0 an increase in oxidation state or decrease? Increase, so is this oxidation or reduction? Can I see hands for people who think it's oxidation? Hands for people who think it's reduction. Okay, so from -1 to 0 is going up in oxidation state, so that means it is oxidation. Okay, I know it's been a little while, so hopefully this is going to be helpful. Oxidation. And here from +6 to +3, is that going down or up? Down, so this is reduction. Perfect. So, the thing that is reduced, and the thing here, so the thing that's oxidized is my I-. The thing that's reduced is my CrO42-. Even though the chromium's oxidation state is what's going down, we still have to remember that it's this whole compound that gets reduced. So the answer would actually be CrO42- gets reduced. And remember, guys, that if that thing is reduced, that thing is the oxidizing agent. And if something is oxidized, it is called the reducing agent, okay? It's a flip there, so be very careful. It's easy to mix those up. Okay, and down here are the rules for assigning oxidation states. So hopefully that'll be really helpful for you guys. do know that that's going to be an important part of your exam, so make sure you practice that, okay? Let me see here. Oh, sorry. Okay. So for this one, lithium and nitrogen react to produce lithium nitride. How many moles of lithium nitride are produced when 4 moles of lithium react in this fashion? So for this, it's actually, I'm going to go through this really quickly. It's actually just a matter of using dimensional analysis. They tell us that they're asking how many moles of lithium nitride are produced, oh sorry, I'm on the wrong sheet. Lithium nitride are produced when we have a certain amount of lithium reacting. We can assume here, if they're giving us only information about one of them, that we're talking about the limiting reagent. We don't have to like worry about any excess. So here, we can just go for using our 4 moles of lithium that they give us, using the equation to convert between moles of lithium to moles of lithium nitride. So here, 6 moles of lithium and 2 moles of lithium nitride. Here, and they ask me for, how many moles, so I just go for, I solve that out, and I get 0.133 moles. So this question I put up as kind of a reminder that being able to go from some amount of something in a reaction to some amount of something else is really important. You guys need to make sure you can use that equation to convert from the moles of one thing to the moles of something else, okay? That might come up several times in your exam. For this problem, which of the following is insoluble in water? Okay, to do these problems, it's just a matter of memorizing the solubility rules, okay? And those are really easy to forget, so make sure to look over those. There are some general rules. Anytime you see Na plus, Li plus, or K plus, or NH4 plus, or here we also have NO3 minus, C2H3, O2 minus. No matter what, if you see these in a compound, those compounds are always soluble in water. It doesn't matter what you're paired to. Okay, so this is like a really awesome way of kind of knocking out quite a few different problems. So this is just one piece, but this is like one of the major pieces to the solubility rules. So here, if I look in my problems, I have an NH4 here, so that means it's soluble. Here, remember Na, I have my Na here, so that is soluble. And if I have this thing, C2H3O2, which is found here, that is also soluble. So I'm left with here A and D. And if we remember, OH compounds are usually insoluble unless they're paired with a few different things. Unless they're paired with calcium, barium, or strontium. So here this is calcium. So this is kind of like, in general, it's insoluble unless it's paired with these exceptions. That is actually an exception, CaHO2, so that is actually soluble. So a lot of people would go for this one because OH compounds are usually insoluble. But this is an exception, and the answer is actually this one. So make sure you guys review the solubility rules as well. And for this problem, it's a similar thing. You just look at the solubility rules. I'm going to skip this one just so that we have more time. And here is a sheet with the solubility rules in your review. So make sure to go over it and get familiar with those concepts. Okay, for this problem, you guys probably did this in your last chapter, in chapter 5. I know a lot of you guys just had exams on it, so hopefully it's still a little fresh, but this can be particularly confusing, so I wanted to make sure to put up a problem. So, there's actually a formula for this, but before we get started, the general concept of this Does anybody know what this thing is called? A J-tube? I think usually I hear it called a manometer or something, but I think J-tube is another word for it. Oh yeah, here, a mercury manometer. And what the manometers do, or the J-tubes do, is here we have some kind of gas in a container, and it's putting a pressure on the mercury here in this tube. And we also have some pressure from the atmosphere going in the other tube. And those two pressures are competing with each other. The atmospheric pressure and the gas pressure are pushing against each other. And one of them is going to be usually stronger than the other one. Sometimes the level of liquid is exactly the same, and the pressures are exactly the same. But here, which one is stronger? The pressure of the gas or the pressure of the atmosphere? Perfect, the gas. If you look, the liquid is more pushed down on the gas side, showing that the gas is pushing a greater pressure or has a greater force on the liquid. And so we can actually use the difference in liquid levels, here the 29.2 centimeters, to find how much stronger the gas is. So the formula for this is the pressure of gas is equal to the pressure of the atmosphere plus or minus the how great a difference there is between the two levels of liquid in millimeters. Okay? Something to note, usually you'll see the difference given in centimeters, and you need to convert to millimeters. Okay? The equation uses plus or minus, because sometimes the gas is less powerful, and sometimes the gas is more powerful or has a higher pressure. In this case, which did we say? Which is a higher pressure, the gas or the atmosphere? The gas. So that means the pressure of the gas is going to be equal to the pressure of the atmospheres, or the atmosphere. Is it plus or minus a little? Minus, I heard a plus. The answer is actually, it's plus a little. Because remember, the gas is more powerful. So the gas pressure is the same as the atmospheric pressure plus some amount. And that amount is the difference in millimeters of mercury. Again, the plus is because the gas is more powerful or has a higher pressure. So if I plug this in, they told me that the atmospheric pressure is 749. So I'm going to plug this in. And I'm going to convert here from centimeters to millimeters. And that is going to be 292 millimeters. And again, I'm adding because the gas in this case is stronger, as a higher pressure. If it was reversed where the atmosphere had a higher pressure, would I add or subtract? Subtract, exactly. Make sure you guys know the difference between those two. And when I get here is 1041. And that is D. Any questions about that one? Yes?
So in what case would you subtract?
That is a great question. So here, do you see how on the gas side the liquid is pushed down more? Does that mean the gas has higher pressure or the atmosphere? Perfect. So I put a plus. If instead the liquid was lower on the atmosphere side, what do you think I would put? A plus or a minus? Then I would subtract, because here the gas pressure is equal to the atmosphere pressure. In that case, it would be minus a little bit. In this case, it's equal to the atmosphere pressure plus a little bit, because it's greater. Does that answer your question? Awesome. Okay, in this problem, it's a density problem. And for this problem, we need to remember that the formula for the density of gas. Could somebody tell me what's the formula? Here, density of a gas is equal to What? Okay, I heard mass over volume. D equals m over v. That's the standard density for like any compound. For the gas, or for a gas, there's a particular formula though. Okay, I heard molar mass times what? Times pressure over what? R times T. Okay, so for this problem, you're going to be using this formula. I'm going to skip this one too. If we have time, we'll come back to it, but I just want to make sure we can get through all the different stuff. Let me see how I'm doing on time. 15. Oh, actually, you know what? I will do that problem. I was able to catch back up because it was about 15 minutes behind, but now I'm back on track. So let's really quickly do this one. What is the volume I need to be using? Oh, wait, sorry. Liters, do I even need a volume for this one? Oh, I know. Okay, so first of all, let's look. We need molar mass and we need pressure. Are we given a pressure? Yes, 780 torr, which is the same as here, 1.03 atmospheres. Okay. And the molar mass, I'm not given the molar mass in this problem, but I think I can find that. Let's see here. Am I given a temperature? Perfect, here 3703. When I convert to Kelvin, I get 310. And, oh yeah, okay, so what's the only thing I don't have in this problem? The constant, I'm not given the constant, but I know what it is. Okay, what is the constant? Perfect, 0.08206. What is the only other thing I don't have now? Molar mass, where can I find molar mass? Solve for it maybe, okay, which would be grams over moles. Do I have grams over moles given? What gas am I talking about? NO2. Can I find the molar mass of NO2? Yes. I will say on the ACS, usually that would be given just because I don't want you to spend a lot of extra time calculating molar masses. So I'm going to give it to you guys here. If you add up the molar mass of nitrogen and those two oxygens, you're going to get 46 grams per mole. Bless you. And that is NO2. Okay. So now I have everything I need. I'm going to go and plug in 46 over here. The pressure was 1.03. And 0.08206 times the temperature, which is 310. And what do we get when we do that? I heard 1.86, which grams per liter. And that is answer choice C. Any questions about that one? Oh, sorry. Any questions? Okay. So guys, we are an hour into the review. So if you haven't started, I'd say now's the time to go ahead and fill out that evaluation, okay? So while we're going through the next few problems, they're going to be more concept related. So now is a good time to pull out that survey I gave you and just start going over it. Yeah?
Can I get one?
What was that?
Can I get one?
Oh, yes. Thank you so much. Does anybody have an extra survey? Can I see hands? Okay, so could you guys just pass it down this way, the extra surveys? Thank you, guys. You guys can keep that one. I think this is enough. Okay, can I see hands for who does not have a survey? Oh, everybody there? Here you go, man. Anybody else? Okay, thank you guys so much. I'm going to leave a stack here, so if anybody else needs them. But yeah, I'd say now is a good time because we're going to be going over a few concept-related stuff. So not as heavily involved in like math and stuff. Okay, so for this next one, arrange the following gases in order of increasing average molecular speed. Do you guys remember which is going to be a faster gas? One that's heavier or one that's lighter? Yeah, the lighter the gas is, the faster it can move. So, if I order these in the order of speed here, I'm going to get A. Cl is our heaviest gas, so it's going to be going the slowest. F2 is the second heaviest. O2 is close to being the lightest, and N2 is the lightest gas of all of these, and so we'll have the highest molecular speed. Okay, and again, we're going to be getting the masses of each by just looking at the periodic table and multiplying by 2, because you see here how every gas there are 2 atoms. So we have to look at the molar mass from the periodic table and multiply by 2. For a previous practice exam that I saw a few days ago, the professor did something really tricky. Instead of putting Cl2 or O2, he just said oxygen gas, chlorine gas, and he didn't give you that there were 2 atoms, and so it changed the answer. So make sure you guys are extra careful here when they say oxygen gas or chlorine gas, that you know, oh, those are diatomic. I need to multiply by 2. Because sometimes they'll compare it to things like neon gas and xenon gas, which are not diatomic. Those are noble gases. So remember, that'll change your answer when you're looking at how big that thing is. So just make sure to pay attention to the wording and things like that. Okay, in this example, or in this problem, it says an ideal gas differs from a real gas in that the molecules of an ideal gas, and then it has a bunch of statements. Here, the E says, so we're asking for which one is true of ideal gases. And E says they have an average molecular mass. That actually is not, so this is picking on your understanding of the kinetic molecular theory, which is here. And ideal gases don't have an average molecular mass, but they do have an average kinetic energy. So that's trying to trick you with that one. The average molecular mass has similar wording. Make sure you guys are very familiar with the different concepts for this. Here it says they have no kinetic energy. That wouldn't make sense because if they have an average kinetic energy, they have to have some kind of kinetic energy. So they can't be 0. So D isn't true. It says here, oh, sorry guys. It says that they have a molecular weight of 0. We know that that's not true. Gases don't have a molecular weight of 0, even ideal gases. Here they have no appreciable molecular volumes. So this is kind of a tricky one. Gases do have volumes, but I think maybe Dixon mentioned this, gases fill whatever space you put them in, so people sometimes say they don't have a real volume because, they can have any volume, so it's not a defined volume, but they do have a molecular volume. This problem, depending on who you're asking, it could be maybe different answers, but at least in this case, we will say that they don't really have an appreciable molecular volume because they can really fill up any space they want. So they don't really have like a set defined molecular volume. And for this problem, have no attraction for one another. That's actually part of the kinetic molecular theory. It says that the molecules are going so fast and colliding with each other and bouncing off each other so quickly that they don't actually attract each other. It's called perfectly elastic, or here completely elastic. And so in this case, they have no attraction for each other because they're completely elastic. So that's the answer to the first one. Or that's the answer there for 17A. For this problem here, 10 grams of argon and 20 grams of neon are placed in a certain volume of a container at a certain temperature. and they say the partial pressure of neon is what? What do you guys think we might need to use for this? If we're given a lot of information about a particular gas, what is usually the first place that we go? The ideal gas law, perfect, which is PV equals nRT. And what am I solving for again? Pressure. So I'm going to go ahead and rearrange this. Pressure is equal to nRT over V. And which gas am I looking at, argon or neon? Neon, perfect. I have some amount of grams. I'm going to need the moles though. So how do I go from grams to moles? Yeah, the molar mass, perfect. So here, let me go ahead and do that. Got my 20 grams of neon. My molar mass is 201.8. And that's going to give me actually just about 1 mole of neon. Oh, I'm so sorry. Sorry about that, guys. I was like, something seems weird. Okay, perfect. 20.18. Sorry about that, guys. So this is the molar mass of neon. And 20 divided by just about 20 gives me 1 mole. Okay, so when I plug this in to get the pressure, I'm just going to plug in my 1 mole. Remember, my R is 0.08206. And my temperature here, I'm going to go from our 25, and I need to convert to what? Perfect. Kelvin, so 298. And my volume is here, but I need to convert to liters, so this is 1.20 liters. I can do this by just moving over the decimal place 3 times, or if you want, you could use dimensional analysis for this. It's really whichever one you're more comfortable with. Okay, and that will give me 20.4 atmospheres. And that is answer choice A. Any questions about that one? This one's a little tricky because they give you 2 gases. And you might be thinking right away, oh, probably something like Dalton's law, where you add up all the pressures. But in this case, you don't need to do any of that, because they give you all the information about each gas, and they ask you for the partial pressure of one of them. They could instead ask you for the total pressure. Then I'd have to get the partial pressure of neon, the pressure of argon, and add them up to get the total pressure. But in this case, they just asked for 1, so I gave them the one they were looking for. For number 19 here, we have a reaction with some delta H or enthalpy. And it says with this reaction, it is, and they say endothermic or exothermic, and they're asking whether heat is released or absorbed by the reaction. Do you guys remember, first of all, how do we find if the reaction is exothermic or endothermic? What do we look at? I heard the delta what? The delta H, perfect. A negative delta H tells me what? Okay, it's perfect. A negative delta H tells me, I heard someone say it is exothermic. And what does a positive delta H tell me? Endothermic. Okay, so for the first one here, it's negative. So that means it's one of these 2 probably. So not this one, not these 2, because those say endothermic. Now the next part is seeing if you remember what exothermic means. Do you guys remember, is exothermic heat being released or absorbed? Perfect, it's released. The way I remember it, exo sounds like exit to me. And endo begins with En, which is the same as enter. So enter or absorb, or exo, exiting. And here, exiting, so exothermic released. So C is our answer here. Okay, any questions about that one? So for this next one, guys, it's going back to one of the first concepts you saw at the beginning of this semester in Chem 1B, which goes to like emission spectrums and orbital theory and energy levels and things like that. You guys have to know that on the ACS, it's not all math. There's a lot of understanding concepts to it. So make sure you guys go back through the things that you've already done. Dixon especially, he picks on a lot of concept stuff. So even his exams are a great reference, and I think the other professors are as well. All your professors, guys, have actually been kind of preparing you for the ACS throughout the whole semester, because they're going in depth with the details and also the math. That's just like the ACS. It'll ask you about details. It'll also ask you about like math problems. So make sure you understand both sides. Okay, so for this one, which emission line in the hydrogen atom spectrum occurs at the highest frequency? Okay, so is high frequency high energy or low energy? I heard some people kind of mumbling it. Okay, high frequency is high energy. Okay. And so here, if I have, let's say that this line is energy, and I have a bunch of, here I have a bunch of energy levels, or my N levels. Here, let's say this is N equals 1. This is the line energy level for N equals 1. N equals 2. N equals 3. N equals 4. What do we notice as we're going higher up? Yeah, it's getting smaller and smaller. There's a smaller difference in energy levels. Yeah, and remember, guys, also that as N goes up, as your N or your principal quantum number goes up, the energy level is going up. So if you see here, that's what we see with the N1 to N4 here, we're going up. And as you increase, the distance between the levels is smaller and smaller. So in these problems, they're asking you which transition from one level to another level is going to give me the highest frequency, or here, the highest energy. Okay, so here I have A, which says from 3 to 1. Here you see N3 to N1. And here I have B, which says 4 to 2. So that's this one, B. This is our A. And then the other ones are a little past the, they're so high up there that I haven't drawn them. Here, are C and D the answers? No, they're super high up, and they're going from a really high number to a slightly less high number. Remember that as we go up really high, the difference between energies is really, really small. So from here, for example, in D, from 10 to 8 is a really small release in energy, and it gives us a really low frequency. So it can't be D. Same with C. From 7 to 5, it's still really high up there. So it's going to give us a really small release in energy. Between A and B, which one gives us a higher amount of energy released? Yes, you see here how big this difference is, so it's going to release a lot of energy, as opposed to B, which releases just a little bit of energy. Okay, so the answer here that releases the most energy at the highest frequency is A. Any questions? Okay. So for this next one here, kind of continuing on this topic from the first chapter you guys saw, we get into quantum numbers, like our principal quantum number and our angular momentum one. We need to make sure that we remember those concepts, what those things mean, and the different principles behind them. Here it's asking us in question 21, which set of quantum numbers is correct and consistent with n equals 3? N equals 4. Okay, so if we think back, whenever we have some n value, do you remember what the possible ranges of our L value was? Yeah, exactly. Here our L could be from 0 to n minus 1. And do you guys remember what our ML range would be? Perfect. From negative L all the way up to positive L. Okay. So for this one, n equals 4. That means that my L can be 0, 1, 2, 3, or 4, right? So far, are we good? Are you sure?
No.
It can't be 4, no. You have to go up to 3, which is our n minus 1, or our 4 minus 1. Make sure you guys are paying attention. Okay. And our ML can be from what value to what value? Here, depending on which one they pick, let's say they pick 3 here, it could be from minus 3, minus 2, minus 1, 0, plus 1, positive 2, or positive 3. Okay? So here, that is if they picked an L of 3. If they picked an L of 2, it would be from minus 2 to positive 2. So you have to remember that the L that they pick tells us which ML values we get. So looking at these problems, n equals 4, remember the highest L value can be 3. If you look at answer choice B here, L is equal to 4. Is that good? No, that's too high, so B is not correct. And let's see for D here. Is my L value okay? Yeah, my L value, looks like I lost my mic. That's okay. I was told that it might die. Can you guys hear me okay? Yeah. I'll make sure to be a little louder now that I'm not worried about like blowing your guys' ears off with this mic. Okay, so here, n equals 4. Is our L value okay? Yeah, here, because it's less than 4, we're good, so L's good. Is our ML okay? Yeah, here, remember, it can be from minus 3 to plus 3, so that's good. Is our MS value okay? What's bad about it? It should be half, so D is not the answer. That leaves us between these two. Let's look at A here. Is our L value okay? What about our ML? Yes, it is. What about our MS? Yes, everything's good there. If we look at our C, though, L is 2. So what's the highest number our ML could be? The highest number could be plus 2, but here I've got a plus 3. So there's a problem with that. This is tricky because here, if you do this, you see that n is 4, so we can have 0, 1, 2, or 3, or we could have any one of these. It's important to note here that because our L was 2, that means that it cuts off the range to only this region here. Okay, so the L that they give you is really important to tell you what your ML values can be. Any questions about that? Okay, so here, this one is just about, if you remember, the order on the electromagnetic spectrum from like ultraviolet and X-ray and things like that. That's going to be something important to like look over and remember. I included a spectrum in this review, so I think it'll be really helpful to look over. For this one, it's asking of the following, blank has the longest wavelength and blank has the greatest energy. So it's asking about two different radiations. Let's go back here. Let's arrange these as if they were on the electromagnetic spectrum. Remember that visible light is the first one you're going to see, going from beginning to end. Then up next we have ultraviolet. Then after that we have gamma. This is arranging it as you would usually see on the electromagnetic spectrum. Do you guys remember, is this going up in energy or down in energy? It's going up in energy. Here, is it going up in frequency or down in frequency? It's going up in frequency. Remember, higher energy, higher frequency. So it's also going up in frequency. And here, is this going up in wavelength or down in wavelength? Down. Perfect. So here, this would be the opposite one for our wavelength. Okay, and if we look at this, it's asking us which of the following has the longest wavelength. So if I look, I have to go this direction, and that would be which one? Perfect, visible light, so that means I can cancel out this one, and this one, because the first one visible for those two. Okay, up next here, it's asking about the greatest energy. Which one has the greatest energy? Perfect, gamma. So visible, gamma, there's D. I like it way better without the mic because I was like trying to speak really quietly, but now I can kind of speak loud. That's much better for me. Okay. What color of visible light has the highest energy? Remember, we just talked about how energy is going up. There's a really, really helpful trick in remembering the order of light within the visible spectrum, which are the colors that we see. What is that acronym? Yes, Roy G. Biv, which is red. What's the next one? Indigo and violet. I've never seen like indigo put up there. It's usually violet, but who knows? Make sure you know indigo is there too. Okay? Okay, indigo, I heard someone say, what is indigo? It's like a lighter version of purple. It's like a bluish purple. So hopefully that answers your question. And it is actually right about here. Indigo is like this color. So if you guys see here, Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. Remember also the order of here increasing energy, increasing frequency, and decreasing. When you go up, it's decreasing wavelength. So you have to go this way to increase your wavelength. And here it says, what color of visible light has the highest energy? That would mean here, we're talking about violet. And here, violet. Do you guys see that? Any questions? Okay. On to the next one. So for this one, the wavelength of a photon that has an energy of this is, so they're asking me for the wavelength and giving me the energy. Is there a formula that relates the energy of a photon and its wavelength? You can answer yes or no for this one. Yes, there is. Do we remember what it is? Okay, here I heard E, and it's E of photon, equals, what was that? HC over I think there is one for like V. We're talking about the wavelength one. And wavelength is the last component. There are like, I think 3 or 4 of these formulas that's really short. It's really easy to mix them up. So make sure you guys make a little list of the formulas you need to know. And make sure to rep them until you feel really comfortable using them. Okay? It's really easy to forget these. I will also say, maybe check online and see if you're given these for the ACS. I don't think you are. I think you're going to have to memorize these. So keep that in mind as you're going into the exam. You're going to want to have these memorized. And here, I'm solving for wavelength. So I'm going to go ahead and rearrange this, switch out my E and L, and get HC over E. Okay. So now, I'm going to go ahead and plug in energy of photon. Didn't they give me that? What is the energy of the photon? 6.33 times what? Perfect. And that's joules. And that's dividing here H times C. What is H? I do think you guys are going to be given that, actually. I'm almost sure. So I'm going to give it to you here. H, what is the name of H? What is it? What's Planck's constant, perfect. And it's 6.626 times 10 to the negative 34th joules times seconds. And what is C? Speed of light, do you guys know this? 3.0 times 10 to the 8th meters per second. Perfect. And that gives us a wavelength of 3.14 times 10 to the negative 8 meters. I will say, keep in mind, oftentimes they're going to be asking for wavelengths in nanometers, because nanometers gives us a really nice whole number usually, one that isn't really big with exponents at the end. So make sure you can convert from meters to nanometers, okay? Because they might ask you instead to get the nanometers, and then you have to convert from this guy to nanometers. And the answer is B here. If you look, this is the closest answer. I know that our number is slightly different just because of different rounding maybe, but make sure, usually the number will be really, really close, even if there's, you rounded differently than them. Any questions about that one? Guys, this question could have been so much harder. So make sure to look over, even if you feel comfortable with this, look back and see the other questions that maybe your professor asked on an exam to see what maybe to expect, so that you know this is probably the easiest example of what you'd see. You might see it, or maybe you'd see a harder version. So get practice with both just to make sure. Okay, for this one, the wavelength of light that has a frequency of this is here. Now we're asked to find the wavelength given a frequency. Is there a different formula than the other one? Or is it a different formula than the other one? Yeah, this time we're relating wavelength with frequency. Before we were relating wavelength with what? Energy, perfect. So now we're talking about a different formula. And what formula was that? Oh, sorry, here we go. What formula are we going to be using? It starts with wavelength, and it's equal to what? Speed over frequency, perfect. And let's see here. Okay, so in this problem here, my speed, again, is the speed of light, 3.0 times 10 to the 8th meters per second. And my frequency is 1.20 times 10 to the 13, 1 over seconds. When I solve for this, I'm going to get 2.5 times 10 to the negative 5 meters. And that is answer choice B here. Any questions about that one? Oh, yes. Say that one more time. Oh, yes. Okay, so make sure you guys are familiar with the symbols too. I don't know how they could test you on it, but you want to make sure you know, like, here, I wrote a V there. That's actually frequency. I didn't mention that. Here, I don't know if I'm writing the symbol, like, perfectly accurately, because maybe it has, like, a few little swirls here and there. But in general here, V is the frequency, okay? It's the symbol for frequency. I think it kind of looks maybe more like this. But here, I'm not the best at drawing out, you know, all the different Greek symbols. But here, make sure you guys know V frequency, lambda is wavelength, C is speed of light. What was H again? Planck's constant, and then E is energy. Okay. For this next one, we're almost done here. We have about 20 minutes left, and I should be able to get through all the problems, I think. So, 20 minutes before I'm going to start going into question time. So here, for this one, it's asking for the ground state electron configuration of Mn, or manganese. So you're going to have to go back to what we started from the first chapter we did in this semester, and go back to finding the electronic configuration for some element. Do you guys remember when we did this in class, we usually started from the previous noble gas and then counted up from there? But in this example, they go right down to the bottom. So here they're not going to be going down to the previous noble gas, so make sure to take a note of that when you're like trying to figure it out. You have to go from the very beginning all the way up to the element. So for this problem here, our manganese is right over here. So remember that when we're doing the electronic configuration, in this example, we start from the beginning. So we start with hydrogen. So I'm going to go ahead and do it out with you guys here. What would hydrogen, let me see if I can do it up on top of each other. So here, what's the first thing I have to write? What group are we in? S, P, D, or F? Perfect, S. What energy level? 1. Here, the top row is 1. So here, I have 1, S, and I'm going here, hydrogen. Go over here, helium. Remember, guys, helium here, technically, for these problems, belongs right over here. So hydrogen, helium, that's our 1s. How many did I go through? 2. Perfect. 1s2. Then I go to my what? 2s2. 2s2. Go through these two. Then I go over here, go across to my 2p, 1, 2, 3, 4, 5, 6. Remember, I'm trying to go all the way up to magnesium over here. So my 2p6. Okay. Now I'm going back down here to my 3s2. Here from 3s1, 2, I get to my 3p1, 2, 3, 4, 5, 6. So my 3p6. Now to my 4s2, perfect. And onto my, what was that, Rico? 3d. Remember, guys, when we get into the D block, we go down 1. So here from 4 to 3. 3d, and I count up to 1, 2, 3, 4, 5. Yeah? Oh, perfect. Okay, something you guys have to take note of. On your ACS, usually they're going to arrange these numbers from lowest energy to highest energy. When we do it out, we have our 4s2, and then we do our 3d5. Which is higher energy? Perfect, 4s2. It's the one with the highest n, or the highest quantum number in front, which is 4. So when you see it on the ACS, it will likely be switched around. So these two guys will be swapped. So keep that in mind, because if you don't know that, it's going to be really hard to find the one that you're looking for. Okay? If you look here, B, 3D 7, we're using 3D 5, so B is not right. Here, we've got our 1s2. Looks like everything's good here. This is probably the answer. Let's go through the other ones. Let's see here. Do you see, guys, here 4D5? Remember, it's 3D5. Do you guys remember I told you how the ACS, if it's a common mistake, it'll be an answer choice? This is a prime example. You see here, let's say somebody forgot to go down one and went to 4D instead of 3D. That would be the answer they pick. This is an actual old ACS problem. This is from the ACS review test book. Okay? So I hope this shows you guys that you really have to review. Because I know sometimes on exams you could be like, oh, it's multiple choice. You know, I'll eliminate the ones that aren't right and kind of figure out the rest. This, if you get something wrong, you'll get an answer for it. Okay? So it's not the same as usual. So make sure to very thoroughly practice this. So 4D5, and in this case, they don't have any D. They went straight to the P's instead, which is another common mistake. Instead of going to D, they just like, oh, P's next. That's wrong. And that leaves their only answer choice as D. Okay. For this next one here, we're talking about concepts again. Remember when we talked about filling up electron orbitals, we had Hund's rule and the Pauli exclusion principle and the Aufbau principle. Okay, this is going to be testing you on that. So, is this good? No. Why not? What's wrong with this? Perfect. Hund's rule tells me that every orbital gets filled up first with one spin, and then you come back around and fill up the next ones. Okay, here, this violates Hund's rule. They could say, what rule does this violate? Okay, so make sure you also know the different rules. Here, is this okay? What's wrong with this? Yeah, so this actually violates Hund's rule because they didn't fill up everyone they could, and they have the same spin. So Hund's rule is violated, and it's called the Pauli exclusion principle. Okay? So violates those two. Okay, so those are not correct. Here, in this case, is there anything wrong with, let's go to B first. Is there anything wrong with B? What's wrong with B? They have the opposite spin, yeah. So I don't know if there's a rule for this where you have to fill up the same spin, but this is not the standard way of doing it. In practice, when you guys have learned this, the standard way that chemists have done it is they go up every one, come back around and do down every one. There's no rule for that, but that is the way that it's done, and so that is actually why it's wrong. Somebody early this semester asked me if that's okay, and I said technically not because it's not traditional, but technically there are no rules against it. If you guys see here, this is actually incorrect because standard is not this way. You start by filling up everything with one spin and then come back around and fill everything with the opposite spin. So this is the correct one. Okay, for this one here, as atomic number increases from 11 to 15, the atomic radii of the elements does something. I remember I got this one wrong. This was one of the easiest questions because it's literally, do I know my periodic trends? Okay, make sure you guys look over these because there will be periodic trend questions and they should be pretty straightforward. Those are like free points. You just have to remember what the trends are. In the review, I included a table with all the different trends except here for electronegativity, which is this right here. So electronegativity, I'm going to say En. Make sure you guys review these. Okay, these are really important and pretty much are free points. So in this example, I'm going to draw out a makeshift periodic table. Here, the atomic radii, the trend is this way. So here, if this is my periodic table, if I go to the left and down, I'm increasing my atomic radii. Here, if I look on the periodic table from 11 to 15, this is how it looks. So let me show you guys. Here, Na is 11. Up to 15 is P. So you see I'm going opposite the trend. So as the atomic number increases from 11 to 15, the atomic radii, what? Decreases. And that's the answer. They could technically, you see how it says increase and then decrease? If they do it where like, maybe they were talking about one of these ones where you've got 34 and then you go up to 36 and then also come back around to like 38. It might be the one where like, oh, you increase and then decrease. But I don't think I've seen those standardly. It's usually just to trick you. So look into that carefully and just make sure that you answer it, appropriately. Okay, so for this one, greatest electron affinity, again, just looking at the electron affinity trend is right here. So it's asking which is the greatest electron affinity. So if I do the periodic table, this is the electron affinity trend. And if I order these halogens, it's going to look like F, Cl under it, Br under that, and then I under that. It's asking for the one with the greatest electron affinity. So what's the answer? Perfect. F. Any questions? Awesome. Okay. We've got just a few more questions left and about 5 minutes before I start questions. Okay, I want to point out that I made a mistake, guys. So I included the answer choices to all these problems on the back of the review. The answer that I put for this one, I put B, but it is actually not B. The answer is, let me see, it's D. Okay? It is not B. Okay, I actually, when I was doing this problem, I looked over it. I was like, oh yeah, I know that, and I put the answer choice, but I also got tricked by a very common trick for this problem. Okay, so be very careful. So make sure, guys, going back in the review, go to the very back and change the answer, because I have the answers on the back. So for this problem, lattice energy is dependent on two things. Do you guys remember what's one thing? Yeah? Yes. The first thing is their charge. So I'm going to say lattice energy, E, depends on firstly, the charge. Do you want a big charge or a small charge for a good? You want a big charge, yeah, for a strong attraction. And actually, guys, charge is the most important factor. So let's say you have a conflict between charge and size. Charge is the one you go with. Okay, so it depends on charge and size. Remember, we want our charge to be big, and we want the size of the atoms to be small or big? You can think of it like a magnet. Which is going to have a stronger attraction, when they're far away or really close? Really close. And to get really close, atoms need to be really small. Okay? So small is what we want. Here, if we look at our periodic table, I can't go too in depth to this problem because we're almost out of time. But if I look at the combos between the pairs, let's see BE and O. I was fooled because here, BE and O both have here a -2 charge and a +2 charge. When all the other examples, except for one, has like +1 and +2. Here these have 2, but what I didn't see was D here. Look at our calcium down here and our sulfur down here. Do you see here how between B and D, I'm going from O to S and BE to calcium? So which one is better, the BEO pair or the CAS pair? Yeah, the CAS pair, because even though they both have really good charges, they both have that +2 and -2, the CAS are the smaller bunch. Because remember, the trend is down and to the left for atomic radii. So because I'm going down, they're getting smaller, making them have a stronger attraction and a better lattice energy. Any questions about that? Yeah?
Doesn't size work like when you go down and then to the left it gets bigger?
You're right. It does. So as I go down, it gets bigger. So actually, my original answer was right. So guys, so sorry. When you go down, does it increase in size or decrease? Increase. Do I want it small or big? Small. So which pair, BEO or CAS? Yes. So let's switch these around. Okay, guys, I want to let you know that was literally me tricking myself 2 times in a row. Okay, I'm sorry. That wasn't a setup. Sometimes I throw in the wrong answer just to help us think. That was literally just, oh, I got it right the first time, thought it was wrong now. Thanks for the help, guys. So the answer is actually B and not D. So the original one is correct. So don't change anything. I'm really sorry about that, guys. And thank you for catching me and speaking up. I really appreciate that. Okay. So we have time pretty much for this last one. And I'm happy because this is one of the harder ones. So remember, guys, when we are trying to find the molecular or electronic geometry, there are some steps we need to follow. The first step, and this one is asking for the shape. Again, guys, if you haven't filled out the review, now is the time, okay? So go in and really quickly fill out that review. So the first step is to count up the number of valence electrons. Here I've got 1 nitrogen and how many fluorines? 3. Perfect. 3. So if I look here, that's going to give me 3 times 7, or 21, and 5 valence electrons for nitrogen. If I add those up, I'm going to get here my 26. And now I go ahead and try to draw the molecule as symmetric as possible. So NF. Remember, guys, central atom is usually the one that is most electronegative or least electronegative. Least electronegative. And here, if we look at the periodic table, nitrogen is least electronegative. Each bond is how many electrons? 2. If I use 3 bonds, I used up 6 electrons, so I've got 20 left. I'm going to put 6 around each fluorine to complete the what? To complete the octet, yes. Here this gives me 1, 2, 3, 4, 5, 6, and 7, 8 around this fluorine, this one, this one. That leaves 18. And now I have 2 left. Where do I put those last 2? On the perfect central atom. Here, how many electron groups do I have around this? 4. Perfect. Which gives me what electronic geometry? Perfect. Tetrahedral. So, is the answer D? Why not? Because molecular geometry is more specific and tells me it is trigonal pyramidal. Okay? So, C. Remember, guys, you can relate the type of orbital here, type of hybrid orbital, to the tetrahedral geometry. So if I have 4, or to any kind of electronic geometry. So I've got 4 groups. That tells me that what is my hybridization. Hybrid is, what's the hybridization for this, guys? sp3, perfect. And on the back here, I included, oh, here we go. Here, this should help you guys out a lot. You guys are going to need to know the angles of each thing as well. Circled in red are the shapes that no matter what are always polar. So for the shapes I've circled in red, it doesn't matter what atom combos you have. If you get that shape, that molecule will always be polar. So that helped me a ton on the exam, because I didn't have to think back to memorizing. I could just be like, this is polar and this is polar because it's that shape. Okay? So this is included in your review. So make sure to go back, know all the angles, know the names of the electronic and molecular geometries. I'm going to open it up to questions in the last 10 minutes, okay? You guys can come up here and ask me any questions or make any comments.
The answer on your answer sheet for 32 is A, but you wrote C.
Oh, okay, so that problem, I was talking about the hybridization for the other problem. I just put in an extra part because I didn't have